So far we've explained the strength of binary acids such as HF compared to other hydrogen halides. Now we're going to go on to another class of acids called the oxoacids. So they have a general form in which they contain at least one oxygen atom bonded to at least one other element, and this central element is bound to other oxygen atoms. And then there's also at least one hydrogen atom bound to an oxygen, and this is because the hydrogen atom has to be lost as a proton in order for the molecule to behave as an acid. So some examples of oxoacids include nitrous and nitric acid. Nitric acid is the stronger of the two, being one of the strong acids. Sulfuric acid and sulfurous acid, again, where sulfuric acid is a strong acid, whereas sulfurous acid is a weak acid. And then perchloric acid, which we also know to be a strong acid, is stronger than the related acids chloric, chlorous, and hypochlorous acid. So if we look at these trends in acids, we see that whenever we have the same central element, the number of oxygen atoms is correlated with the strength of the acid. Specifically, the more oxygen atoms that we have bonded to the central atom, the stronger the acid. And so we want to understand, why does oxoacid strength increase with an increasing number of oxygen atoms bonded to the central atom? So again, just as we did for the binary acids, we want to look at the strength of the OH bonds and the electron attachment enthalpies. Now, one of the big differences between the oxoacids and the binary acids is that the OH bond strengths aren't going to change significantly. So for all oxoacids, the bond that needs to be broken in order for dissociation to occur is an OH bond, and this bond strength isn't going to vary significantly because it's always going to involve an oxygen and a hydrogen atom. And so with that being said, it turns out that the electron attachment enthalpy ends up being the key feature that determines the strength of the acid. So if we look at the bond strength and the electron attachment enthalpy, it turns out that nitric acid, that has the significantly larger electron attachment enthalpy, has a less positive sum of these two enthalpy changes, and so it's a slightly more favorable enthalpy change than for nitrous acid. And so going from HNO2, which has two oxygen atoms bonded to the central nitrogen atom, to HNO3, the acid strength increases. So in this case, the electron attachment enthalpy is the more dominant effect, and the strength of OH bonds between different oxoacids isn't going to vary significantly. So in general, the strength of oxoacids with the same central atom increase with increasing number of oxygen atoms bonded to the central atom. Now, chemically, why is this occurring? If we think about an oxygen atom, it's one of the most electronegative atoms. The only thing that's more electronegative than it would be fluorine. And so if an oxygen atom is bonded to the central nitrogen atom, it's removing electron density from this nitrogen atom, which in turn removes electron density to the OH group that is also bonded to the nitrogen atom. And so having more oxygen atoms is going to increase this effect. So more oxygen atoms means more electron density removed from the OH bond. And so that's going to increase the affinity of the oxygen bond to hydrogen for electrons. And so as the number of oxygen atoms increase, the electron affinity of the oxygen atom is going to increase. And so it's going to be even more favorable for the OH bond to break and essentially give one of the electrons from that bond to the oxygen atom. Another way to think about the strength of oxoacids is to consider the stability of the conjugate bases that form when they're deprotonated. And so generally speaking, oxoacids are stronger when the anion created by loss of a proton can accommodate the negative charge. And so in order to accommodate the negative charge, there are a few conditions that need to be met. If the anion can exist in multiple resonance forms, this means that it's going to be more stable because it can delocalize the electron density from that negative charge into multiple forms throughout the whole molecule. And then also if the central atom has a high formal positive charge, that's going to stabilize the anion, the conjugate base that forms. forms. So let's look at the anions that form for if nitric and nitrous acid react as acids. So for nitric acid, we can see that if we draw the Lewis structure, this is one Lewis structure that we can draw, but there are actually two different resonance forms that we can draw. And so there are three different resonance structures, and so this means that when nitric acid is deprotonated, the negative charge that results can be delocalized throughout the entire molecule. And so for nitric acid, the nitrate ion that forms has three resonance structures and a formal charge on the nitrogen of 2. Now if we instead consider the nitrite anion that forms from nitrous acid reacting as an acid, this also has multiple resonance structures, but in this case there are only two different resonance structures, and so there's slightly less delocalization because there are fewer ways to delocalize the charge. And additionally, the formal charge on nitrate is 1 for the nitrogen atom, and so that's going to stabilize the negative charge less than in nitrate, which has a formal charge of 2 on the nitrogen. And so in this case, in all cases, the conjugate base that forms has to be quite stable in order for it to be favorable for that to form. And so the more stable the conjugate base, the stronger the related acid. So the last class of acids that we're going to consider are carboxylic acids. So this is a large class of organic acids that all have a form similar to acetic acid in that they all have the carboxylic group. And so they're collectively called carboxylic acids. So let's think about why the carboxylic acids are Bronsted acids. So the carboxylic group is this CO2H group, and it's found in all carboxylic acids. In this case, we're just looking at the simplest case, which is acetic acid. So to start off, we see that there are two different kinds of hydrogen bonds within the molecule. There are carbon-hydrogen bonds and there are OH bonds. Now we've seen before that carbon-hydrogen bonds are essentially nonpolar. The electronegativity difference between carbon and hydrogen is quite small, and so they're essentially nonpolar bonds. So even in water, the carbon-hydrogen bond is not going to be cleaved to form a proton in the resulting conjugate base. But we have a polar oxygen-hydrogen bond, and this can be broken by when that one of the hydrogens interacts with a nearby water molecule. So essentially in this reaction, water is reacting as a Bronsted base, and the carboxylic acid is reacting as a Bronsted acid, donating a proton to water to form hydronium and this carboxylate anion. And the carboxylate anion can be used to help explain why carboxylic acids are acids, and the reasoning for this is that they're resonance stabilized. So there are two different resonance structures that can be drawn for the carboxylic acid, and so again, in forming the carboxylate anion, in being an acid, the carboxylic acid forms an anion that's quite stable because its negative charge can be delocalized over one part of the molecule rather than being localized on a single atom. So the acidity of carboxylic acids can be increased if an electronegative substituent replaces a hydrogen atom. So all carboxylic acids are going to contain alkyl groups, the simplest being either a methyl or an ethyl group, and we can think about substituting some of the hydrogens on these alkyl groups with an electronegative substituent. In this case, we'll look at substitution of acetic acid, so where this group is just a methyl group, and substituting some of its hydrogens with chlorine atoms. And so we can see that as we increase the number of chlorine atoms that are replacing hydrogen atoms, the pKa value decreases, meaning that the acid strength increases. So these electronegative groups are also quite electron withdrawing, so they remove electron density from the OH bond, and this increases the electron affinity and the electron attachment enthalpy for the oxygen atom, and so it's more favorable for that OH bond to break because the oxygen atom then gains an electron. So to summarize, for binary acid, the strength of acids in the same group of the periodic table increase down the group. The strength of acids in the same period increase moving from left to right across the periodic table. Oxo acids with the same central atom become more acidic as the number of oxygen atoms bound to the central atom increases, and carboxylic acids become more acidic if more electronegative substituents replace the hydrogen atoms in the alkyl group.